water is flowing into and out of a large tank. So maybe there's some sort of tap that's helping it go in, and then perhaps a plug hole or something where it's going out. Initially, the tank contains 10 liters of water, so that is T equals 0, V equals 10. And we're told that there are V liters at time T, and that water enters the tank at this rate here. So that is actually going to be dV by dV in by dt. That's the rate of change, that's the rate of increase due to it entering. But it's also leaving the tank, so that's going to be dV out by dt. And this is proportional to the volume of water remaining, so I'm going to write that down. And then dV out by dt is going to equal, now I'm going to make it minus kV. If you make it kV, it's okay. And then it's going to work out even if you added kV on later on, but I'm expecting it to be negative, so I'm expecting k to be a positive constant here, k greater than 0. We're also given then that when t is 0, the volume is decreasing at a rate of 3 liters. So I can add to my initial condition and write dV by dt when t is 0 is going to be minus 3. Remember, rate of decrease, it's decreasing at a rate of 3 means the rate of increase is minus 3. Make sure you get that sign in correctly. And then got to show that the volume satisfies this equation. So dV by dt will be the sum of dV in by dt and dV out by dt. So I'll get 3 minus 4 over 1 plus e to the 0.8t. And then I can write minus kV. And if you end up writing plus kV, it's not going to matter. K is just going to be slightly different for both of us if that happens. Now we can sub in our initial condition. So it's going to be minus 3 is equal to 3 minus 4 over 2, because e to the 0 is 1, which then becomes 2. And then v is 10, remember, so we're minusing 10k. And that means 10k is going to be 1 plus 3, it's going to be 4, so k is 0.4. And hence dv by dt equals 3 minus 4 over 1 plus e to the 0.8t minus 0.4b as required. Next up, we're asked to determine the derivative of arctan of e to the 0.4t. So you might know the derivative of inverse tan of x, and it's going to be 1 over 1 plus x squared. It is actually in the formula book, so we can quote it if we want. So for us, we're going to get, right, we've got to use the chain rule here. So we're going to deal with the outsides, just arctan to the something. So I'm going to get 1 over 1 plus e to the 0.4t squared. Because I just basically forget about this bit, but I replace x by it. And then I times by the derivative of the inside, which is going to become 0.4 e to the 0.4t. And that will therefore become 0.4 e to the 0.4t divided by 1 plus e to the 0.8t. Now in the mark scheme, they split that 0.4 up into 2 over 5. You've got the numerator with 2 in and the denominator with 5 in and multiplied. I actually think I know it's a decimal, but I think this is a little bit simpler, so that's how I left my answer. Just a little reminder where this derivative comes from. I think, when you're doing these papers, not under time conditions, it's always worth just reminding yourself about these things. So if I had y equals inverse tan of x, and that is arctan, of course, and I wanted to find dy by dx, then this is how we do it. We could rearrange it so it's tan y equals x and actually find dx by dy. And for this one, you either have to use the quotient rule or you might know the result. It's sec squared y. Okay, so I'm not going to go to that level of detail and use the quotient rule. Okay, so now I want to get it back in terms of x. Well, we've got to use an identity. Sine squared plus cos squared is identical to 1. If I divide through by cos squared, I'll get tan squared plus 1 is sec squared. So I'll get it back in terms of tan now. It's going to be tan squared y plus 1, which is actually going to equal x squared plus 1, because remember, tan y is x, and therefore dy by dx is 1 over x squared plus 1. I definitely wouldn't go back and do this one from first principles. I would use the chain rule. So once you got that result, it's fine to use the chain rule. But just a reminder, that is where this formula comes from. We're now asked to solve the differential equation from part A and determine an equation for the volume, giving our answer in simplest form as V equals f of t. So here we go. Here's the differential equation. Now we can't use separation of variables here because, there's lots of reasons, but like if we would be able to do it if it was that, okay, that would be okay. But because we've got a 3 minus that function, okay, it's out of the question. So we've got a different method. We're going to be using an integration factor here. The first thing we're going to do is write it as dv by dt plus 0.4 v is equal to this function on the right, 3 minus 4 over 1 plus e to the 0.8t. Now we need to multiply both sides of the equation by e to the power of the integral of 0.4 with respect to t. I'm just going to remind you where that comes from, okay? But that is something to remember. This here is our p of, it's p of t here. But I'm going to write it down a little bit more generally. Let's say I had dy by dx plus p of x times y is equal to q of x. So I know when I differentiate a function times by, let me do it down here. If I differentiate y times by some sort of function, then I would get dy by dx f of x plus y times f dash x. So I want to basically take this equation up here and times it by f of x, a suitable f of x, such that I can write it back like this, because then I can easily integrate it, whereas I can't integrate that left-hand side as things stand. But I'm going to multiply through by f of x. I get dy by dx, f of x, plus p of x, f of x, y equals q of x. And if I now compare them, well, this is the same as this. This must therefore be the same as this. And if that is going to be, I'm basically ensuring that that is the case. I can now write down that p of x, f of x, y is equal to y f dash x. Cancel out the y's. That means f of x over, wrong way around. F dash x over f of x is going to equal p of x. If I integrate this, both sides with respect to x, then I would actually get ln f of x over here equal to the integral of p of x, which means my suitable f of x is going to be e to the power of the integral of p of x with respect to x. I'm just deriving this, showing you where it comes from. I'm not expecting, you shouldn't be doing this in the exam. I'm just saying that is how we get our integration factor. We write it as dv by dt plus something times v, and then that is going to guide us towards our integrating factor. And this something is my p of x, or in this case p of t. So I'm then going to find e to the integral of p of t dt. That's where that bit came from there. So you can just literally go straight to here. I just wanted to clarify where that comes from. So actually, we're going to be timesing by e to the 0.4t. And let me bring this down. I'll keep all that there. So I will get dv by dt times e to the 0.4t plus 0.4 e to the 0.4 t equals 3 e to the 0.4 t minus 4 e to the 0.4 t over 1 plus e to the 0.8 t. And this thing here is looking a lot like something we had before. But before I look up, I'm just going to keep going with this. So I can now write down that d by dt of v times e to the 0.4t, this is precisely what we times by that integration factor, because I can bring it together like this, is equal to 3e to the 0.4t minus 4e to the 0.4t over 1 plus e to the 0.8t. And I can now integrate both sides with respect to t. The left-hand side is going to become v e to the 0.4t, because I'm just undoing the derivative, just takes us back to v e to the 0.4t. And that is going to equal 3 divided by 0.4. Actually, that becomes 7.5. And then e to the 0.4t. In fact, I'm not going to rush it. Hold on, let me just put the integral sign there, because I haven't quite got the second one in the right form. Let's just take a look at what we showed earlier. We showed that when we found the derivative of arctan of e to 0.4t, we got this. So it is exactly the same as what I've got, except it's a 0.4 rather than a 4. Okay, so I'm going to write 0.4. Therefore, I'm going to need to times by 10. I've divided the numerator by 10, so I need to put a times 10 on the outside. Okay, just that extra step. Right, let me do this now. I get 7.5 e to the 0.4t, and it's going to be minus 10 arctan, or we could write tan to the minus 1, arctan of e to the 0.4t. Then don't forget your plus c. That must be there. We're very close. Now we can write down that v is equal to 7.5, because I'm dividing through by e to the 0.4t, minus 10 to the e to the minus 0.4t. Okay, I am dividing by e to the 0.4t, but it's equivalent to times and by e to the minus 0.4t. Arctan e to the 0.4t plus c times e to the minus 0.4t. Okay, we just got a little bit more to do, because now what did we have? We had a condition. It was so long ago. So it was that t equals 0, v equals 10. That's going to help us find c when t equals 0, v equals 10. So 10 equals 7.5 minus 10 times e to the 0. Well, that just becomes a 10 here. And then I've got arctan of e to the 0, which is 1, plus c times e to the 0. That's just 1 again. Therefore, c is going to equal 10 times arctan 1. Now, inverse tan of 1 is actually pi over 4. So we get 10 pi over 4, or 5 over 2 pi, and then plus 2.5. And finally, we're there. v equals 7.5 minus 10 e to the minus 0.4t arctan e to the 0.4t plus, I could bring the 2.5 out if I wanted, plus 2.5 times pi plus 1. If you don't do that, don't worry about it. E to the minus 0.4t. Pretty epic. Well done. There's one part to go, and we're told after 10 minutes, the volume of the water in the tank was 8 liters. Evaluate the model in the light of this information. So let's work out what the model predicts when t equals 10. And if you sub it in, definitely just put this into your calculator. We're going to get 7, but it will be expected you leave your answer up here in terms of pi and everything. So you'll be careful because if you just put it into your calculator, you might know where to deal with it. Yeah, we get 7.405. Now, this is not that far away from 8, but it's also not that close. If you were to work out the percentage error, then it would be the error. It would be 8 minus 7.405. And then you would divide by the true value, which is 8, and times by 100. And we actually get a 7.43% error. That is not a good error. And therefore, um, model is not reliable. You don't have to do the percentage error. You can just say it's not that close. Of course, you could say unreliable or not reliable. Well done.